All right, so the recording is on, and let me just review with you what I'll be doing today. It's the last official day of teaching in terms of new material. This is it, last day for that. So today we're going to finish up chapter 10. And again, I'm not going to go through the PowerPoints. I'm posting the PowerPoints, but I'm not going to go through them because it would be better if you read the chapter on your own. You may even want to look for some YouTube videos out there, but follow along. I'm going to show you the steps of how to actually do hypothesis tests today, step by step through examples. I think that's the best way for you to learn how to do this and understand what you're doing. All right, so let's go through the PDFs again. And once again, I have created several PDFs here. First one was I went over last time, was the, let's see if I can move this out of the way here, was basic facts about hypothesis tests. So this just gives you an idea of what the null and alternative hypotheses are, how to write them, the assumptions that we make, that the null hypothesis is initially true, and then that there's two decisions, either we reject or do not reject the null hypothesis. When we do that, there are two different errors that we can make. Now, if your decision is to reject the null hypothesis, when we go through the 6-step process, and that is your decision to reject the null hypothesis, the only type of error that you could make is the type 1 error. Because the type 1 error is when you reject the null hypothesis, and the null hypothesis is really true. So just remember that if you ever see that on a test, you're going through the whole process of doing a hypothesis test, and then it asks you what type of error did you commit, all right, or possibly commit. I'm not saying commit, but possibly commit. If you reject the null hypothesis as your decision, then the only type of error that you would have committed was the type 1 error. If your decision was not to reject the null hypothesis, the only type of error that you could have made was the type 2 error. Makes sense, right? So these errors only occur after you've actually run the hypothesis test. Now, you don't really know if you made the error or not because it's an unknown population reality, whether the null hypothesis is true or not. If you knew ahead of time whether it was true or not, there's no reason to do any of this. But we don't know that, so we're making a hypothesis or a guess of what the null hypothesis is. Then we take our sample and run through the 6-step process of the hypothesis test. And then we make that determination. Do we reject or do we not reject the null hypothesis? At that point, we can determine what type of error we could have made. Also on the right here is the basic definitions of the different probabilities that come about through this process. Alpha is the probability of a type 1 error. It's also called the level of significance. And it's something that the researcher sets up front. This is the level of significance I want for my test. In other words, this is the amount of type 1 error I'm willing to tolerate. Beta is the probability of a type 2 error. Again, you don't need to know anything more than that. Just know that we want that obviously to be low, and we want alpha to be low also. And 1 minus beta is the power of the test. That's the probability of rejecting the null hypothesis when the null hypothesis is really false. Well, that's a good thing, and we want that to be as high as possible. Notice that the power of the test is the complement. It's 1 minus beta. It's a complement of the probability of the type 2 error. So you should know that, all right? And that's all you need to know. You don't need to know anything else about these. It's a little bit of sophisticated to actually go in and calculate beta and calculate 1 minus beta. But if I do give you beta, all right, then the power of the test is just 1 minus beta. All right, just know that. And that's obviously could be a multiple choice type question I could ask. And again, it's right on this page right here. Make sure you know that. And then the 3 types of tests. Now, again, 2-tailed test, left-tailed test, and a right-tailed test, right? And it all depends on what? The alternative hypothesis. If the alternative hypothesis is not equal to, has a not equal to sign in it, it's a 2-tailed test. And then what you're doing is you're going to use your sample mean to calculate what's called a test statistic. I'll show you how to do it in a minute. And then you're seeing what is the probability of getting that that sample mean in this case, or something even further away from the proposed population mean, the null mean. All right. And in the two-tailed test, whatever area that you calculate, you multiply it by 2. Because each tail of the two-tailed test is 1/2 the p-value. And up here, I do give you the definition of the p-value. All right. Now, this is all in your book, but I'm trying to organize it so it's all on just a couple of pieces of paper, which you can again print out and you can refer to instead of searching throughout your book, which is not a good idea with this. All right. If you're not familiar with this that much, you haven't done a lot of problems with this, then it's better to have a summary next to you. And I'm doing it for you, make it easy. Right? Left tail test, the alternative hypothesis has less than. So you're going to find the area to the left of the sample proportion in this case. And then the right tail test is going to be greater than symbol as the alternative hypothesis, and therefore you're going to find the area to the right of the sample statistic. All right. Again, I'll show you the steps of doing this. So I'm going to show you both a left tail and a right tail test, and then if there's time, we'll search for a two-tailed test in the book, find one, and then I'll give you that one to actually. I'll just ask you a couple of questions about it. Again, if we have time, but definitely in the homework when I post the homework, there will be an example of a two-tailed test in there also. All right, and then last time we went through the 6-step hypothesis test for population proportion. I went through the 6 steps with you before we left. All right, show you how to do all 6 steps. And again, we're going to use an example to show you how to do this one. Then I created a separate one that I'll post, 6-step hypothesis test for population mean. And then in this PDF here are two examples of a hypothesis test, one for the mean and one for proportion. Right. Let's just take a look at the 6-step hypothesis test for population mean. Since I didn't I just created this and I'm going to post it, but you haven't seen it yet. Step 1 is basically the same as the step 1 for the proportion. If you go back to the proportion, you could say state the null and alternative hypotheses. You're going to use P for the proportion, population proportion. Right? And with the mean, notice that you're going to use U for the population mean. All right. So you have to recognize the difference between a mean and a proportion. I think in most cases it's pretty easy here. Proportion is dealing with counting and taking a proportion of the number of people surveyed. You're counting the number of people who are answering a certain way to a question, something like that. And you're counting the number of people who answer yes, let's say, to a question as opposed to no. And then dividing that count by the number of people who ask the question to. And that's your proportion. A mean has to do with something we're measuring: height, weight, time, money, whatever it might be. It's something we're measuring. So I hope that's really clear to you, the difference between those two. Now, step 1, again, you're going to state the null and alternative hypotheses, just something like this. All right, you're going to write null hypothesis. I like to use the word versus because it's a competition between the two hypotheses. And then we do HA and then do the alternative. Step 2 is the assumptions. The assumptions, the first assumption here is always that the sample's randomly selected. Now, obviously, if it's not randomly selected, then the wording of the problem is going to tell you whether it's randomly selected. It's either going to say random selection of the sample, or it's going to say something like, make the assumption that the sample is a representative of the population. Well, the only way to do that is through random sampling. So that statement means random sampling. So in the final exam, and also in the test too, but test is multiple choice, but in the final exam where it's the written part of it, and it's asking for assumptions, make sure that's one of the assumptions, you're right, because you lose a point. You lose some points if you don't write that down. All right. And the second assumption, well, for a mean, if it's a hypothesis test for a mean, then there's something called the central limit theorem. It says the following. It says if the population parameter, whatever, if it's a mean, the population parameter is normally distributed. If the population is normally distributed, then the sampling distribution is automatically normally distributed, and it doesn't matter what the sample size is. We're assuming normal distribution for the population, and the sample size could be any sample size, because the sampling distribution is going to be normal also. However, if there's nothing mentioned about the distribution of the population, or it states that it's skewed or not normal, then we have to have a minimum sample size. And the minimum and that most people use is 30. So the sample size needs to be at least 30. If it is at least 30, then you don't have to worry about what the population looks like. You can just assume that the sampling distribution is approximately normal. So once again, you have to say the sample is randomly selected, if it is, obviously, if it's true. If it's not randomly selected, you can't do any of this, by the way. The whole process doesn't work. And the second thing has to be, we want to test the assumption that the sampling distribution is normal. Well, if the population is normal, sampling distribution is automatically normal. If the population, if there's nothing being said about the population, or it's stated that it's not normal, then we look at the sample size and make sure it's at least 30. That is only true, by the way, for the population mean. We go back to the hypothesis test for proportion. Notice that step 2, the second part of it is different. It says for the proportion, we multiply n times p and also n times 1 minus p, n meaning the sample size and p being the hypothesized proportion. We multiply those two numbers, and if it's at least 10 for both of these calculations, then we say that the sampling distribution of sample proportions in this case, is normal. So notice the calculation is different here. Many students mess this up on a test. They'll say, oh, the sample size is over 30. No, not in this case, not for proportions. And that's why you need to print this out and actually look at it step by step when you do a problem, when you do a hypothesis. If you don't do that and just think about, rely on memory, you might get it right and you might get it wrong, and then it's too bad. Because if you just had printed it out and had it next to you, then there shouldn't be any issues. You just read it, and the steps are simple. This is not, calculus here. This is not quantum mechanics. This is elementary statistics. This is an elementary. I don't mean to be funny about it, but it is elementary compared to what you will see later on if you ever take more advanced statistics courses. This is very basic. But being very new, and it's a new language, it's not something that's easily understood at the beginning. So that's why I created these handouts. Now, if you don't use the handouts, that is your choice, but I've created them for you to make this process easy. So let's get back to the sample mean, the hypothesis test for the population mean. And step number 3 is the test statistic. Now, if you go back to the proportion for step 3, this is for proportions. Remember, it was pretty easy. It was just basically one calculation. This is for the sample. This is for testing the population proportion, right? P hat is your sample proportion. Subtract the null or hypothesized proportion, and then take the square root of p times 1 minus p divided by n, where p again is the hypothesized proportion. You calculate this, and then, let's now go back to the mean. Look, it's more complicated. All right, a little more complicated for the mean, because there's 2 formulas here, and you have to make a choice. Which one do you use? This is where, again, students make mistakes right here. All right. Now, I'm stating when we're dealing with a hypothesis test for a population mean, one of the assumptions has to be whether we know the population standard deviation. Now, normally we don't in real life. But if the problem does give you the population standard deviation, then the test statistic is going to be a z. And it's going to look familiar to you. It'll be the sample mean minus the proposed or hypothesized mean divided by the standard error, the denominator. Standard error is the standard deviation of the sampling distribution of sample means. That's called the standard error. You need to know that, by the way. So if you're not, it's in the book, but if you're not familiar with it right now, it sounds foreign to you, write it down. The standard error is the standard deviation of the sampling distribution. Standard error for a mean, if you know sigma, this population standard deviation is sigma divided by the square root of the sample size, square root of n. This whole thing is in the denominator. Now, if sigma is unknown, and this is the typical case, if it's unknown, then we have to replace the sigma with s. And when we do that, we've now calculated a t statistic. Right? Numerator is exactly the same. The denominator is just s, the sample standard deviation. Now, the s is referring to the sample standard deviation for that sample, that one sample that you have. All right, that's what it is. All right, and if you have data and you're asked to find this, you just put in the data into a list, and it'll give you both the sample mean and sample standard deviation. We'll go through an example just like that. But you calculate a t. All right, it's a t, not a z. So if sigma is unknown, you're calculating a t. Now I'll put in an asterisk next to it so that it's clear that this is a number that we're calculating versus a variable. All right, this is a number. All right, so you're going to get some number out of either one of these calculations. So you have to make your choice. Now, if the problem says nothing about sigma and gives you information about s, then you're going to do case 2. All right. But if they do give you information about sigma, you do case 1. All right. So that's step 3. What's step 4? Calculate the p-value. Remember, the p-value is the probability of getting that sample statistic or something more extreme than that when we assume that the null hypothesis is true. All right. The null hypothesis value is true. So that's what the p-value is referring to. It's the probability that we use our calculator to figure out. Now, if we have case 1, that is, we know sigma, we've calculated z star here, sample the test statistic. Then, if we're doing a two-tailed test, remember what a two-tailed test is. Let's go back to this one right here. Two-tailed test is when we have the alternative hypothesis saying not equal to. And the test statistic, by the way, is either going to be bigger than the hypothesized mean, or the test statistic is going to be smaller than the hypothesized mean. I don't mean test statistic. The sample, in this case for a mean, the sample mean is either going to be bigger than 10 or smaller than 10. Period. Now, if it's bigger than 10, we're going to do a right tail calculation for the probability. And if it's less than the mean 10, we're going to do a left tail calculation. But if it's a two-tail test, whatever probability we come up with our calculator, we have to multiply it by 2 because we have to assume that either one of these is possible. Either you're going to get a left tail or a right tail probability. So we have to, whatever answer we get, we multiply it by 2. All right, that's only true for a two-tailed test. Again, you have to make this really clear in your mind. The two-tailed test is multiplication by 2 only occurs in that case. All right, so let's go back to where we were. So if sigma is known, and we're going to use the z statistic, then our p-value is going to be 2 times, and we're going to use normal CDF with our calculator. And if z star is bigger than 0 in this case here, which means, remember, when we go to a z, when we convert to a z, we now are in the world of the standard normal with a mean of 0, standard deviation of 1. So the mean is 0. So if z star is actually bigger than 0, it means it's bigger, it's to the right of 0. And we're going to calculate that area to the right. And that's what this normal CDF is doing here, saying 2 times normal CDF, and the first number we put in is our calculation of Z star. And then we do comma 1,000, and then 0, comma 1. This is the standard normal. All right, so we do 2 times that normal CDF, and we get our answer. Now, if Z star is less than 0, then we're going to do a left tail here calculation. It's going to be 2 times normal CDF, and this is left tail, negative 1,000 on the lower endpoint, and then Z star upper endpoint, 0, comma 1. And then that's going to be what you would do if you had it. Now, Z star less than 0 means it's negative, right? That's what it means. So negative Z, you know, and if you're going to find the area to its left, that's what you want. And then 2 times that will be your p-value. If Z star is positive, then we're going to find the area to the right of that, and then we multiply that by 2, and that's our p-value. So it depends on whether Z star is positive or negative. You choose one of these 2. That's why you have to follow along, all right? The homework will give you practice with this. All right, if it's a left tail test, that means let's go back to the basic facts one again, left tail test. That means that the alternative hypothesis is less than. That means we have area to the left that we're trying to find for a p-value. So if there is a left tail test, then we use normal CDF, and we're going to use the left tail. Now, in this case, the whole area that you find is the p-value. You don't multiply this by 2. It is just one area. That's the p-value. If you have a right tail test, once again, let's go back to this PDF. The area is going to be to the right this time. That's a right tail test. That's because of the alternative hypothesis having greater than the right tail test. Right. Then we use the normal PDF. Here. There we go. All right, so normal CDF, and then we use 2 times, excuse me, not 2 times. We'll use normal CDF Z star, comma 1,000, comma 0, comma 1. All right. All right. Now, show that to you. Well, now that's only for case 1. That's when sigma is known. So this is where a decision has to be made. You make this decision in step number 3, right? Which case do you have, case 1 or case 2? So you don't even need to actually make your choice here. You've made your decision up here when you calculate your test statistic. Either you pick case 1 or case 2, depending on whether the population standard deviation is known or not. Now, suppose the population standard deviation is unknown, then you've calculated a t statistic. And then again, the same thing. If it's a 2-tail test, p-value is 2 times. And in this case, you're not going to use normal CDF. You're going to use t-CDF. And by the way, all of you, including those of you who have the 83 calculators, you all will have t-CDF on your calculator. So the p-value is 2 times. Again, 2-tail test, you're going to do 2 times. t-CDF, and once again, if t star is greater than 0, if it's positive, it's going to be right tail that you're going to calculate here. So it's t star, comma 1,000. Notice, however, that the third number that you put into your calculator is degrees of freedom. And what is degrees of freedom? Look at the bottom here. It's next to this note. It's n minus 1. It's the sample size minus 1. That is degrees of freedom. Again, if t star is negative, less than 0, then we do a left tail. It's 2 times the left tail. t-CDF negative 1,000, t star degrees of freedom. Okay? And then again, same thing with left tail and right tail, except again, we're going to use t-CDF instead of normal CDF. And again, we put them in the same order. If it's left tail, we put negative 1,000, comma t star, comma degrees of freedom. And if it's right tail, we put t star first, and then positive 1,000 degrees of freedom. All right. So that is generally how you calculate the p-value. Again, once you've done a couple of these, to sort of know what to do, to know what part of this chart to look at. And then you just, again, I'm going to do 2 examples during class, and I think I might have time for a third, which I haven't figured out, but we'll look for one that is a 2-tailed test. But anyway, that's the first 4 steps, and then step 5, step 6, and step 7 is the same as in the all hypothesis test. Step 5 is your decision rule. Once you calculate your p-value, you compare it to your level of significance. This will be given in the problem, by the way. It'll say alpha is equal to, it'll say level of significance, it'll say probability of the type 1 error. They all mean the same thing. It's alpha. It's whatever that number is. And remember, if your p-value is being expressed as a decimal, you can, and the alpha is being expressed as a percentage, you convert the percentage to a decimal by dividing by 100. All right. Sure, all of you know that. That's just basic arithmetic. If the p-value is less than or equal to alpha, we reject the null hypothesis. P-value is greater than alpha, we do not reject the null hypothesis. That's a decision rule, period. All right. And then step 6 is your interpretation and using the context of the problem. So you're going to say at the blank percentage significance level, S is referring here to significance level, all right? It's not referring to standard deviation. Please don't think that's standard deviation here. I'm just putting that S in there, but it's going to be some percentage, all right? And it's going to be given in the problem. That's alpha. So whatever alpha is, you're going to put it in here. So that's the way you would start writing it. And then you say something like there is enough or not enough evidence. So enough evidence means you're rejecting the null. Not enough evidence means you're not rejecting the null. Okay? All right. Now, alternatively, you could say something like there's enough evidence. If you're going to reject the null hypothesis, you could say there's enough evidence to support the alternative hypothesis. Now, the important thing is here, you're not going to say null or alternative hypothesis in step 6. I don't want to see those words at all. I want you to say, in the context of the problem, what you're rejecting. What claim is it? What is the claim, and whether you're supporting or rejecting, whatever it might be. That's what you're going to write in step 6. Right? You're not writing null or alternative hypothesis. If you write it there, you're just repeating step 5. And if you do that, you get no credit for step 6. So in the final, and where this applies, by the way, is the final exam, when you're actually writing an interpretation. All right. So when you write it, you have to write it in this type of format. And again, I'll show you examples when we go through the 2 examples in a minute. All right. But you have to write it in the context of the problem if you're going to write an interpretation. And that's a 6-step process. So the best thing to do is again, show you examples. So the first one is a hypothesis. Oh, I spelled hypothesis wrong. Hypothesis. All right, but you know what it means, hypothesis. Hypothesis test for population proportion. All right, and we're going to go to exercise 10.29. Let's now go to Cengage ebook, and here's 10.29. This is in section 3, chapter 10, exercise 29. All right, it says in a survey conducted by careerbuilder.com, employers were asked if they had ever fired an employee for shopping online while at work. Of the 2,379 employers responding to the survey, 262 said they had fired an employee for shopping online while at work. Right? Suppose that it is reasonable to assume that the sample is representative of employers in the United States. Well, that little statement there is saying that the sample, we're assuming the sample was selected randomly. All right, so you look for a random selection or a statement like that, and that's part of step 2, right? Where you say, because of that little statement there, we're assuming random selection for the sample. All right, let's look at the question. It says, do the sample data provide convincing evidence that more than 10% of employers have fired an employee for shopping online at work? Well, that's a claim, isn't it? All right, that's the claim. right now. There it is. All right. Now, where's the sample information? Can somebody tell me where's the sample information in this problem? You got to know how to do this, folks. All right. I'm sorry. You just really not. And if you're not paying attention because your video is off, it's not going to do well in the rest of this course. I'm telling you.
Is it the 262?
All right. What's 262 referring to?
The number of employees fired.
Right. Well, no. 262 is not the number of employees fired. What's 262 referring to?
It's the number of employers who said they fired someone.
That's right. It's the number of employers who answered on the survey that they have fired an employee for shopping online at work. That's what it is. Now, what's the 2379 representing?
The number of employers in the survey.
Yes, that's your sample size, folks. That's your sample size. 2379 is your sample size. 262 are the number of people who said yes to this question. That means everybody else said no, but we're only interested in the yeses. This should be familiar to you. This is like a binomial. Remember binomial? Where there was two choices? So many people being asked a question, and so many people said yes, and so many people said no. We're only interested in the yeses here. That's the successes. Remember successes and failures? The number of successes is 216 out of 2379. Said yes to this question. All right. Now, that is P hat. Now, here's where a lot of students also make a mistake. They say P hat is 262. No, that's your count. That's a count. P hat is a sample proportion. So P hat, the sample proportion, is 262 divided by 2379. That's your sample proportion. Now, sometimes in these types of problems, they'll give you the sample proportion, they'll give you the sample size, and they'll just give you the sample proportion, which is fine. Then you know what it is. But many times they won't give it to you, and you have to do this little bit of a calculation. You have to divide those two numbers. All right? But this is not, again, this is not calculus here, folks. This is just basic arithmetic. When you're trying to find a proportion or percentage of something, you take the smaller number, put in the numerator, bigger number in the denominator. Right? 262 out of how many? 2379. All right. Now, I don't want to keep repeating this, but again, I have experience and I know students mess this up right here. All right. I've seen it before. So please don't make that type of mistake. Because if you do the null and alternative hypothesis, then you can really mess up. All right. Now, what other information are you given? You're given the null and alternative here. The only thing, now, you say, well, there's no null hypothesis. Well, it's implied. It's implied because they do give you the alternative hypothesis, which is the claim. The claim is more than 10% of employers have fired it. All right. Is there convincing evidence that more than 10% of employers have fired an employee for shopping online during work? That is the alternative hypothesis. That's the claim. You see? That's not the sample. Not that information there about 10% would have been determined before this research was done, before the sample was done, before we had any sample data. We would have had that question. And then you do the sample and all of that. But that wouldn't have been, that sample data wouldn't have even existed when this research question came about. That's why the research question has nothing to do with the sample. It has everything to do with the population. So let's look at what I wrote down here in my solution for this. You need to follow very carefully what I'm doing. Number one, I wrote that, and this is something you should probably do when you do a problem. Just write down what's given. 2379 is your sample size. even though they didn't say that, they didn't use those words. But if they say 2,379 people were surveyed, that is your sample size, that's M. Look at p hat, 262 divided by 2,379. I rounded it to 5 decimal places. I'll show you with the calculator how you can do this. And I'll show you, let's show you right now, because this is a little trick with your calculator. Calculator is very powerful, and you want the calculator to do as much of the work as possible. All right, so stop sharing. Let's go to the calculator and pay attention to this, because it's a very useful little tip. Suppose you want to save p hat because you're going to use it later in a calculation. You want to save all the digits, because sometimes you'll have, all the digits displayed. It could be 9 digits there. Instead of rounding it, what you can do is do your calculation. So that's what I'm going to do. I have the main screen here. I'm going to type in 216 divided by 2,379. Hit enter. Okay. Was it 216 divided by 2,379? Is that what it was? I think I wrote it down wrong. Hold it a minute. Let me stop, go back to the problem. No, I don't know why I said 216. It's 262. Is that right? 262?
Yes, that's
Yes,
correct.
that's correct.
That's correct. And I have no idea why I wrote 216. So ignore what I just said about 216. So let's go back and back to the calculator, and I'll just erase what I just did here. So clear that out. And we're going to do 262 divided by 2,379. All right, there it is. Now I rounded it to 5 decimal places just when I wrote it down, but you can save this into memory. And how do you do that? On your calculator, on the first column here, right near the bottom, it says STO. That means store. And what you can do is store numbers in alpha characters. In alpha characters. That's the way this calculator works. So I'm going to hit the store button. Now, what is it going to store? It's going to store the answer. The answer is that last number that popped up here. So you did your calculation. That's the answer, right? So answer is going to be stored where? I'm going to hit the alpha button. And I like the letter T for some reason, but you can pick any of the alpha characters on your calculator. You see them right above the buttons. And the T is right above the 4. So I'm going to hit 4 here. Notice the T shows up. And then after I hit enter, what I just did here was I stored this number 0.1103030 into the alpha character T. So when I do a calculation later, I can simply type in T, and that will represent that number. Now, that's a very convenient thing that you can do with your calculator. And I try to teach this to all my classes when I'm doing it in person, but it's hard to do it when we're doing it online. But I'm showing you now. Now, I've stored that number into T. And suppose now let's go back to our problem. Okay. The other thing that was given in the problem is alpha. It said 0.01, I believe. Could have said 1%, but it's 0.01. So it's a 1% significance level. That means that the researcher's saying, I'll accept, if I reject the null hypothesis, I'll accept a type 1 error 1% of the time. I find that acceptable. All right, that's what you're stating here. Now, step 1 is stating your null and alternative. Remember, the problem tells you this, the claim is that we want to see if the true population proportion is greater than 10%. So that's your alternative hypothesis. P is greater than 0.10. Obviously, since we always use equal to in the null hypothesis, that's going to be P is equal to 0.10. The numbers always have to match. All right, so even though they didn't say null hypothesis or any other hypothesis, that's going to be the null. That's going to be the null. All right. Typically, in these problems, they just give you the alternative hypothesis. Step 2. Now, since this is a hypothesis, now we already know since we're using P here, that we're dealing with a proportion. So for step 2, to determine normality of the sampling distribution, we have to calculate NP and N times 1 minus P. And in this case, they both are well above 10. So since, and this is the way you should write it up on your final if you're being asked this, since NP, if you have to show your calculations, just like I've done here. Show your calculations. Exactly like I showed you here, you get full points, all right? So I'm showing you what you should do. Don't skip steps. Don't say, I don't feel like doing this. You might not get any credit. You don't feel like doing it. Just do it. It's not a big deal. Just do it. Since NP and N times 1 minus P are both greater than or equal to 10, then the sampling distribution of sample proportions is approximately normal, period. Now you have to say something about random selection also. Remember, we talked about that. And it says in the problem, it says, since the problem states, and I put in parentheses and I put ... it is reasonable to assume that the sample is representative of employers in the United States, close quote, assume the sample was selected manually. All right, there you go. So I've now completed step 2. I've mentioned that the problem in some way stated random selection, and number 2, it shows you through this calculations here that the sampling distribution is approximately normal. Those are the 2 assumptions that you have to check. Random selection and whether the sampling distribution is normal or not. Both those things. Step 3, calculate your test statistic. And once again, let's go back to the 6-step process. And this is the one that's for a proportion. Go to step 3. And there's your formula. It's always a Z, by the way. Always a Z. So for proportions, always Z. There's no T's involved with proportions. Here is the Z formula. It is the sample proportion in the numerator minus the hypothesized proportion divided by the square root of the hypothesized proportion times 1 minus the hypothesized proportion divided by the sample size. This whole thing is your statistic, your test statistic. Here it is again. And by the way, just giving you a hint here, on your written part of the final exam, you get automatically full credit if you show everything you see here. So don't just show me the numbers. If you just give the answer, you don't get full credit. I'm telling you up front. They're looking for this. You show the formula, you plug in the numbers, and you give the answer. All right? This is full credit right here. Now, if you make a mistake, then you'll get full credit for everything else. See what I'm saying? But if you just show the answer, not only are you not going to get full credit, but if the answer's wrong, get no credit. So please follow these steps. I'm showing it to you. It's a little bit more work, but the point of taking the test is to get a good test score, right? That's what you want. You just do that little bit of extra work, just like I showed you here. This is the answer here. And by the way, you could store this number too if you wanted to. It doesn't matter. All right. Now, why would you want to store this number? Show you in a minute. You can store that one too. So, by the way, let's go back to the calculator. Now we've stored this sample proportion in the calculator. We could do our test statistic right here. This is the way you should do it. Again, I'm showing you step by step, all right? So just follow along. Open us up a set of parentheses. Put your sample statistic first, right? And that's T. It's this 0.1101, but you might as well put T there because you stored it in T. So I'm going to put alpha T minus 0.10, because that is your hypothesized proportion, close parentheses, divide by square roots. Square root of what? The hypothesized proportion. That's 0.10. Do not put T here. You don't put the sample proportion in here. You put the hypothesized proportion here, times, open up a set of parentheses, 1 minus 0.10. Now, if you know it's 0.9, you don't have to do 1 minus 0.10. Divided by the sample size, 2379. Hit enter. There it is. Here's your test statistic. You may want to save that too. Now, you could save it into another variable, another letter if you want. Let's say I want to save it into A, alpha A. So I'm going to hit store, alpha, and A is just above the math button here. You see it, A, hit enter. Now my test statistics in A. So what do I have now? I have two things in memory. I have the sample proportion in T, and I have the test statistic in A. Now you could pick any letters you want, whatever makes sense to you. I'm just doing this randomly, all right? T and A means nothing. It's just letters I'm storing it into. So you pick the ones you want. Now, let's go back to the problem. All right. Now, I'm going to calculate the p-value. Now remember, this is what kind of test? Well, the alternative hypothesis is p is greater than 0.10. Remember, basic facts. When the alternative hypothesis is greater than, this is a right-tailed test. When the alternative hypothesis is greater than, it's a right-tailed test. You're going to find the area to the right in this case here, and that's going to be your p-value. Okay. So let's go back to the handout for a proportion. Notice that it is a right-tailed test. So for step 4, you just scroll down till you see right-tailed test. It's down here. And this is what you're going to write. This is your calculator steps. By the way, as far as grading the final exam is concerned, if you write this normal CDF here and put everything inside of it, full credit, because it's showing me what you did. All right. So normal CDF, you're going to put your test statistic into first position, 1,000, second position, 0.1. That's your p-value. Okay. Let's go down here. What I did, see it? Let's do it with the calculator. Remember, the test statistic is in A. I'm going to do normal CDF in this case, because we always use that for hypothesis tests for proportions. It's a right-tail test, which means I'm going to put the lower here. I'm going to put my test statistic here, and it's A, right? So I'm going to put alpha A. Put 1,000 here. And it's 0.1, it's already defaulting that. Hit enter. And there's my p-value, 0.049777. You can round that to 0.0498. Never round p-values to 2 decimal places. Round it to at least 3 or 4. All right. So I'm going to round it to 4 decimal places, 0.0498. Right. So I now have my p-value. Now let's go back to the problem. The next step. What is the next step? Basic facts again. Or actually not basic facts, 6 steps. So what is step number 5? Decision rule. I'm going to compare the p-value to alpha. And the decision rule says if p-value is less than or equal to alpha, I'm going to reject the null hypothesis. P-value is greater than alpha, I do not reject the null hypothesis. Simple decision right here. Nothing more that you have to do. Back to the problem. Here's your p-value. Here's your alpha. Since the p-value of 0.049 is greater than, alpha is 0.01, it is greater than that, then our decisions do not reject the null. Step 6, here's my interpretation. At the 1% significance level, that's our alpha, there is not enough evidence to support the claim. Now, on this, I'm using the word support the alternative, all right? As opposed to saying rejecting the null. Support the alternative and rejecting the null mean the same thing. Right? There's not enough evidence to support the claim that more than 10% of the employers have fired an employee for shopping online. That's what it's saying. Now, this is, what kind of error, can somebody tell me what kind of error I could have made when I made this decision? Is it type 1 or type 2? This is an exam question, right? So you should know this. It should just pop into your head immediately. What error did you make? Now, you have to have that chart next to you. Probably you don't at the moment, because I just told you today you should. If I do not reject the null hypothesis, all right, what kind of error could I have made? Type 1 or type 2? Come on, somebody just say something, because it's one of those two. If you're wrong, you're wrong. Just take your chance. It's only two choices here. Do you reject? Is it a type 1 error, type 2 error? Just make your choice.
Is it a type 2 error?
That's it. Because a type 2 error is you do not reject the null when the null is actually false. That's why you need that chart next to you also. Okay? I'm telling you, that's points on a final exam. And I'm giving you hints, telling you what you need to know. And just think about it, think about it, why that's the case. All right? Because we're not rejecting the null in this case here. There's not enough evidence to reject the null. That's the mistake we could have made when we make this decision. Now, all of you should make the same decision, but depending on it's based on this one sample. If there was some other sample, you could come to a different conclusion. All right? But based on this sample, you're not rejecting the null hypothesis. All right. By the way, if alpha was 0.05, 5% significance level, what would have been the decision? Would we reject or not reject? Let's change the alpha to 0.05. What's our decision now?
We do reject it.
That's right. So isn't that interesting? It's interesting that it depends on what our alpha is. In many instances. All right. Now, if your p-value is really, really low, it doesn't matter what alpha is. You're going to reject. All right. So if you have a p-value with like 5 zeros after the decimal point and a 2 after that or something like that, you're going to reject the null hypothesis no matter what. That's a strong rejection. But when you have a p-value like this, then it depends on your alpha, what you chose as alpha up front. In this case, you're not rejecting, but if you had picked 5%, you would have rejected barely, right? Barely. It would have been barely below 5%. Okay. Let's look at another example, and we'll run through this a little more quickly because now that you know the steps, it makes sense. This is section 4, exercise 53. Let's go back to the ebook. Right, and we'll go to section 4. Exercise. And this is number 53. Scroll down to get to number 53. The Economist, this is a popular magazine for people who like reading about economics. The Economist collects data each year on the price of a Big Mac in various countries around the world. The price of a Big Mac for a sample of McDonald's restaurants in Europe in July of 2016 resulted in the following Big Mac prices after conversion to US dollars. So these are in US dollars. The mean price of a Big Mac in the US in July was $5.04. So here's your sample data And then they're giving you what happened in the US. For purposes of this exercise, assume it is reasonable to regard the sample as representative of European McDonald's restaurants. All right, so that little statement there says random sample. All right, that's why they're saying it. So that's going to be step 2. Does the sample provide convincing evidence that the mean July 2016 price of a Big Mac in Europe is less than the reported US price? So what is the reported US price? $5.04. All right, can somebody tell me, is this a left tail test? Is this going to be a left tail test, two tail test, or right tail test? From this little bit of a statement at the bottom here. Little that question right at the bottom there. Is it going to be left tail, right tail, or two tail? Look at the question, the very last sentence.
Would it be a left tail?
Yes, right. Because they say less than, right? And what is the number we're going to use for the hypothesized mean?
$5.04.
That's it. So let's go out. Oops, sorry. Let's keep that right there. Hold on. All right, let's go to the solution, a solution PDF. All right. Now, what you have to do, and there's not enough time to do it now, but you all know how to do this by now, I hope, is you take your 12 sample points, because n is 12. If you count the number of values in the sample, it has them all listed, the prices. Put them into a list in your statistical list, and then you go to one variable statistics, and you look up X bar, which is the sample mean, and you look up S, your sample standard deviation. So that's going to be a little exercise you'll do, hopefully today when you get home and do a review of this. Run through this, put those numbers into your calculator as a list, and then go to one variable statistics and look up X bar and S. Now, in this problem, nothing was said about when we're dealing with means, by the way, nothing was said about the population standard deviation. Why is that important? Because of those future steps in the hypothesis test that we're going to be doing. So what's one of the things you look out for? Is there any information about the population standard deviation? There's none. So I'm writing down here sigma unknown. It is a 5% significance level. So alpha is 0.05. So after I've entered it into my calculator, I get X bar and S. I get all this information. And now I'm going to go to step 1, our hypothesis test. Now, again, the only thing they're giving you is the alternative hypothesis, but you'll know what the null is because it's the same number that's used in the alternative. It's a left tail test because they're saying less than mu. We're going to use mu here for the population mean. That's what we use here, not X bar. We use the population mean symbol, mu, Greek symbol mu. Mu is less than $5.04. That's your alternative hypothesis, and therefore you're going to say mu is equal to $5.04 as your null hypothesis. Now, let's do the step 2 because it's a little bit interesting here. Now, if I give you a problem on a test, I can assure you that you're not going to run into anything like this, that you're going to have to do anything like this that I'm showing you here. The sample size is either going to be bigger than 30, or I'm going to tell you that the population is normally distributed, all right? Because that's what the central limit theorem says. That is mentioned in your textbook, the central limit theorem. The central limit theorem states basically, and we talked about this in chapter 8, that for sample means, the central limit theorem says if the sample size is large enough, all right, if the population is unknown or the population is not normal, the sample size is large enough, we can assume that the sampling distribution is approximately normal. And almost all textbooks give the number 30. So if the sample size is at least 30. Now, if the population is normal, is approximately normal, then the sample size doesn't have to be 30, it could be less than 30. Now, in this particular case, the sample size is less than 30 because they only give you 30 numbers in the sample. Only 12 of these prices were given. So we have to determine if the population is normal. Well, the book suggests something like this, and I don't expect you to do this or write this down because it'll be clear in the test itself which way you're going to go. But in this case, I'm doing a box plot of the sample. You remember how to do box plots. If you put the numbers into the calculator, you can do a box plot. And when I do that, well, first of all, when I look at the mean and the median in one variable statistics, I see the mean and median are approximately equal. Now, the sample itself is not normally, it doesn't look normal, but the mean and median are close. And so I'm going to make the assumption that the sample distribution is approximately normal. All right, now, it's a little bit of a stretch in this case here why I'm doing that, but in your test, it won't be. If n is less than 12, or less than 30 in the example that I give you for a hypothesis test for a mean, I can assure you that I'm going to say somewhere in the problem that the sampling distribution is, or excuse me, the population is normally distributed. All right, and it doesn't matter that n is less than 30. However, if I say nothing about n in a hypothesis test, then n is probably going to be bigger than at least 30. All right, so but you're going to write something like that in step number 2. All right, so you're going to look at the samples. You're going to look at to see if the populations is normal. If it says it's normal, then automatically the sampling distribution is normal. If it says nothing about the population, or if it says the population is skewed, then look at the sample size and say, all right, despite the fact that the population is not normal or is unknown, the shape of it is unknown, the fact that the sample size is bigger than 30 or at least 30 means that we can assume the sampling distribution is approximately normal. And we're done. That's it. We also have to say in step number 2 about the fact that the sample is selected randomly, and that the statement here regard to sample is representative of all European McDonald's group restaurants. That is a statement saying that the sample was probably selected randomly. So there you go. All right. So again, in this example here, I did a box plot. I looked at the mean and compared to the median. Well, I'll assure you in other examples that I give you in a real test, it'll be clear. All right. All right. Okay. Step 3. So we're going to assume we can go ahead and do the hypothesis test. Now, since sigma is unknown, let's go back to the steps here. Go back to step number 3. Notice that the test statistic depends on whether sigma, the population standard deviation, is known or unknown. So if it's known, we use the Z formula here. This is the Z formula, Z-score formula. If it's unknown, then we use the T statistic formula, T-score formula right here. Okay? You make your decision right here, and the problem says nothing about sigma. Nothing about it, just gives you data. So if a problem just gives you data and there's no mention of sigma, you know you're going to be doing case number 2. All right, go back to the problem. Step 4. Here is, now it says here, since the alternative hypothesis, it says less than, this is a left tail test. Therefore, I'm going to use case 2 for the p-value. So let's go case 2. Let's look back again at it again. P-value case 2. Well, it's a right tail test, so I'm going to scroll all the way, look all the way down here. Excuse me, left tail test, not right tail. That's the left tail test. So it says if there's a left tail test, this is what I use for the p-value right here. TCDF for your calculator. Open up set of parentheses against left tail. So I'm going to use -1,000. Again, I'm saying T star, that's our test statistic. And then degrees of freedom after that. Okay. Let's go back. And actually, let's go ahead and do that. Let's go ahead and do that. All right. So let's go back to the problem. I think we're running out of time, but that's okay. I do want to show this to you, obviously. You need to know this. So what is our sample mean? It's $3.86. It came out $3.86 even. I don't need to store that. I know $5.04 is the hypothesized mean. That's the one that we're using for the from the US. And here's our denominator. This the numerator here is going to be in our denominator. This ratio here, the numerator of the ratio in our denominator is our sample standard deviation, and we divide by the square root of the sample size 12, and we calculate this to be negative 6.36 approximately. Again, you can store this once you've done this calculation in your calculator. So negative 6.36 is our test statistic. I'm just going to write that down. But again, you can store it if you would like in the way that I showed you earlier, storing numbers. All right, so here it is. Here's your test statistic. And then I'm going to plug it into this TCDF formula here. Let's go ahead and do that with our calculator. Okay. Back to the calculator. Since I'm starting something new here, I'm going to clear this out. And actually, I think I am going to have the right problem here. Yeah, I'm going to do the test statistic here. I'll just do it pretty quickly. All right, $3.86 minus $5.04. And notice I put the numerator in parentheses, all right? That's very important to do that. Otherwise, you could end up with a calculation error here. You're going to end up calculating the wrong thing. So make sure that the denominator you put in parentheses also. Otherwise, you're going to get the wrong answer. Oh, sorry about that. I screwed up. So let's do that again. 386 minus 504. Divided by, open up another set of parentheses. You need to do this when you do this type of problem. I'm going to put in my standard deviation, 0.64265, or
Professor, you put 5.4 is 5.04.
Correct. Okay, so let's go back. Right, if you do that, you can do an insert. Second, insert 0.4. There you go. You insert. Thank you for showing that to me. And then you're going to divide this by, you can hit the division, the square root of the sample size, which is 12. There's 12 numbers here. I'm hitting right arrow to take myself out of the square root, close parentheses, hit enter. There it is. I'm going to store that again in, I'm going to use T. I'm going to store in T. By the way, now that I'm storing into T again, it'll replace whatever was in there before. New value in T. Now I'm going to do that left tail test, right? I have the test statistic here. So I'm going to do, now I'm going to use TCDF here because, again, it's a T. Don't make the mistake of putting normal CDF here. It's TCDF. I'll put negative 1,000 here. Make sure you use the negative sign here next to the enter. That's our negative. I'm going to put T here, right? T. Now, degrees of freedom, what am I going to enter for that? Sample size is 12. There's 12 numbers. What am I going to enter for degrees of freedom? All right, you guys have a lot of studying to do. 11. It's a sample size minus 1. That's what I put in there. Hit enter. Hit enter again. This number here, now tell me, what is this number? Can somebody read out this number to me? That's why I picked this problem, because people will give me the wrong probability here. What is this probability? Can somebody read it to me? You're not familiar with scientific notation. This is 2.68 times 10 to the negative fifth power. The E means exponent. Exponent for what base? Base 10. It's 2.68, 10 to the negative fifth. So you'd move your decimal point to the left by 5 decimal points. Therefore, this would be 0.0000, there's 4 zeros, and then 268. That would be your p value. Okay? Back to the, you need that also. That's for those of you not familiar with that. You need to know that. Oh, I went back to where I was. Sorry about that. Doesn't make any sense. Back to the problem. Okay. Here it is. Very low p-value. You're going to reject the null for sure, but you have to write it out this way. Since the p-value is equal to this and it's less than alpha's 0.05, reject the null. And then step 6, at the 5% significant level, there is convincing evidence that the mean July 2016 price of a Big Mac in Europe is less than the reported US price. Okay? And there it is. That's how you do hypothesis tests. You need to study this. You will not do well, I assure you, on the next test or the final exam if you don't study this. I've given you all the tools that you need. I'll give you homework also. Make sure you have all this stuff printed out so that you can follow along. The only thing I did not show you today was a two-tailed test. But again, if it's a two-tailed test, remember whatever area you calculate using step 4 is 1/2 the p-value. You need to multiply it by 2 to get the true p-value. That's the only thing that you have to remember to do in a two-tailed test. All right? Everything else is the same. All right, any questions? This is a lot of information here, but again, I've laid it all out for you, and it's up to you now to study this and do the homework. And I'll assure you, the amount of effort you put into this will determine your grade, not only for this test and the final exam, but for your overall grade. If you blow it off, don't expect a good grade, all right? It's just, that's the way it is, and I've given you everything you need. So I'm giving you that warning up front. This topic is a little difficult, but if you do the homework and you practice and read the book, you need to read the first 4 sections of chapter 10. If you go through all that, then you'll do fine. You'll be okay. I've seen students do okay with this. But again, it's how much work are you willing to put into this? That will determine how well you do. All right? And again, what will happen next week, next Monday, is a review for this chapter. I will post homework. I'll give you a due date for the homework. Now, the homework will not be, because of my schedule, I won't be able to get it done until late tomorrow. So well, let me think, actually. It actually may not even be till Friday morning even that I'll have it done because of my schedule. It's a little bit rough, my schedule this week, but it will get done, and I will give you sufficient time to complete the homework, no doubt about that. But make sure you do it, all right? Because it's very helpful to do the homework so that you're not surprised by anything, all right? And then we'll have a review next Monday for test number 3. I'll also show you a little bit of how to type information, symbols and things like that into Canvas when you do your final exams. I'll go over that also. And also we'll have a quiz, the Larry Last quiz, which will be cover chapter 10, will be also on Monday. All right, that'll be our last quiz. Next next Wednesday will be our next test, and then our final exam is the following Monday. Remember, you need to let me know ahead of time if there's any issues, any conflicts or anything, and you'll have to take all those things that are coming up early, not late, because I will be grading almost immediately after Monday's test. I'll try to have the grades in by Tuesday, because Some people are graduating and graduation's that weekend. I need to get the grades in early. And also I'm leaving the area. I have personal business with my wife. We have to leave that Thursday. So I need to get everything done beforehand. And please let me know ahead of time if there's any issues, all right? Well ahead of time. But if there's anything at the end of the course, such as, God forbid, COVID. I mean, I've had some students who have COVID, family members, COVID, deaths because of COVID, unfortunately. All those things have happened. Obviously, I will take that into consideration. And you need to notify the university at the end of the semester if anything like that happens. If you're passing the course, you'll get an incomplete. And then when I come back, we'll complete I'll make sure that you complete the course. All right. So that won't be an issue. But please, no other reasons. All right. I don't want to hear about alarms not working. Just make sure that somebody calls you or somebody knocks on the door for these exams and all of that. Okay. So please be vigilant about all that. Any questions? Any comments? Anything? Nothing? Okay. So that'll be it for today. Look out for the homework. I will send you an email when I have the homework ready to be posted. But please, in the meantime, read the chapter. It will be very helpful to read that ahead of time, chapter 10, those first four sections. Don't read sections 5 or 6. I don't know if there's a section 7, but only the first 4 sections. That's all you need to read. And I will post PowerPoints, even though I didn't go through them. You can go through those also. All right, that's it for today. And again, send me emails if there's any issues or any questions.